Buddy, I thought we could take a look, since I won't be here to take homework questions, at assignment number 9, exponentials on parade. I'd like to go through all of the problems. I'm going to go through them kind of quickly because we've spent now 3 days doing exponential problems, and you should be pretty comfortable with these by now. But if not, you can always rewind the video and play it a bunch of times until you're feeling more comfortable, or at least comfortable enough to ask questions. Don't forget, you can always send me questions on the GroupMe about any of these. So our first question on the homework was Tianjin has a population of 10.24 million in 2004. So I'm going to define 2004 as t equals 0. And we said the population then was 10.24 million. And then in 2009, which would be t equal to 5 years later, population was 12.28 million. So when I think about this continuous growth, and I'm not using logistic for any of these problems, I'm just using PERT. When I think about continuous growth here, I think about p equals p sub o e to the rt. And I'm going to plug in my initial amount. That's the amount of population at time equal to 0 for p sub o. I get p equals 10.24 e to the r times 0. Oh, wait a minute. I know r times 0 is 0 and e to the 0 is 1, and so 1 equals that. I'm sorry. I'm just plugging in p sub o, e to the rt. Now I want to use this second ordered pair. That's what I had meant to do. And I'm going to plug this value in for p and this value in for t. So I have 12.28 equals 10.24 e to the r times 5. So I need to solve this equation for r. I'm going to start by dividing by 10.24. And that means I need my calculator handy. So I get 12.28 divided by 10.24, which is 1.19921.875 equals e to the 5r. Then I'll take the ln of both sides. I'll bring down this power with the power rule, and I'll have ln of 1.19921.875 equals 5r. And if I divide both sides by 5, I'll get my r. r equals the ln of that 1.9921875, and then I'll divide that number by 5 to get a rate of 0.03633400606. So my Shenzhen population, my Tianjin population model looks like p equals 10.24 e to the 0.03633400606t. Okay, now we've got this model. I think I'm ready to answer any questions. The question here says, if the city continues to grow at this rate, what will be the population in 2020? So we said that t equal to 0 was 2004. So 2020, t will be 16. So I'm going to plug a 16 in for time. So 16 times that rate, e raised to that power, times 10.24, and I get that the population after 16 years, or in 2020, will be 18.314 million people. That's a lot of people, boys and girls. That's as many people as you have in Los Angeles County, in a city you've probably never heard of before. China has supposedly more than 100 cities with more than 1 million people. The United States, I think, has fewer than 10 cities with more than 1 million people. Keep that in mind. Okay, next question, number 2. Meanwhile, population of Detroit went from 1 million in 1990 to 700,000 in 2011. So we started off at 1990 with a population of 1 million. But I'm going to choose to define this as t equals 0, so this can be my initial amount. And then we're told in 2011, that's 21 years later, so 21, the population was down to 700,000. Okay, so let's build our model. So P equals that initial amount, 1 million e to the RT. And now we're going to plug in this second ordered pair to help us find R. We'll plug in a 21 for T, and we'll plug in the 700,000 for R. 700,000 equals 1 million e to the R times 21. Well, I'm going to divide both sides by a million. That's 6 zeros. These all cancel out. Most of these cancel out, huh? And we end up with 7 over 10, or 0.7 equals e to the 21r. At this point, I take the ln of both sides so that I can bring down the power with the power rule. I'll have the ln of 0.7 equals 21r. And so my rate will be ln of 0.7 divided by 21. As a decimal, the ln of 0.7 divided by 21 is negative 0.016984521. Note, the city population is decreasing at about 1.7% per year. That, we see, is because of the negative. The negative is what tells me that the population of Detroit is decreasing. If I build my Detroit population model, P equals 1 million e to the negative 0.016984521 t. And now I'm ready to answer the question. The question here says, if this trend continues, when will their population be the same as Tucson, or 600,000? Does 600,000 go in for time, or does it go in for P population? 600,000 goes in over here for population. E to the negative 0.016984521 t. How do I solve for t? Well, let's start by dividing by a million. And so I end up with 0.6 equals e to the negative 0.016984521 t. I bet you know what's coming next. We're going to take the ln of both sides here, and we're going to bring this down with the power rule. We'll have the ln of 0.6 equals negative 169. Good try, Mr. Kukla. 169845211 t. Okay, and so what is t? T is going to be the ln of 0.6 divided by that rate, and I get t is 30.07595 years since 1990. Well, if I add 1990 to that, I get that's happening pretty soon. In the year 2020, it's about 2 years from now. If Detroit continues to shrink, we'll certainly be at an equal population with them. Okay, so there's question number 2. Question number 3, carbon parts per million. Okay, carbon parts per million in the atmosphere was 363 in 1997. 1997, we had 363 parts per million. Again, this is my first time, so I'm going to define that as t equal to 0. And then in 2013, well, 2013 is 16 years after this, so 16, the carbon parts per million was 393. Okay, so let's build an exponential growth model because that's what all the data seems to suggest is happening with carbon in the atmosphere. Let's build an exponential growth model for carbon in the atmosphere. I'm going to start by plugging in my initial amount. So we've got Q equals 363 e to the kt. And now I'm going to plug in this second ordered pair for time and quantity to help me find my rate. So I'm going to have 393 equals 363 e to the k times 16. When I divide both sides by this initial amount, I get 393 divided by 363, or 1.082644628 equals e to the 16k. Since I'm trying to find my rate, I'm going to take the ln of both sides so I can bring this exponent down. Then that will give me the ln of 1.082644628 equals 16k. And then I'll divide by 16 on both sides to get k by itself. So if I take the ln of that 1.082644628 number and then divide that result by 16, I end up with k should be 0.00496292236. And I don't know if you noticed this, but this growth rate is really small. This would be 10%, 1%. I'm 0.5%? That's 0.5% of growth rate? It doesn't seem very big. I wonder why so many people are getting so concerned about it. Well, let's see if we can build our quantity of carbon in the atmosphere model. 363 e to the 0.00496292236 t. So here's our carbon in the atmosphere model, and we're asked here, it is thought that 450 parts per million is the point of no return in changing global climate. All right, so here's my model, and I want to know when the quantity is 450. Well, let's figure out how much time we have until we get to irreparable climate change. 0.00496292236 t. We'll divide by 363. We get 450 divided by 363. That's 1.239669421 equals e to the 0.00496292236t. I bet you know what's going to come now. We're going to take the ln of both sides so that we can pull this exponent down in front. All right, so what do we get then? We get the ln of 1.239669421 equals 0.00496292236t. And if I want to know what t is, I have to divide both sides by this rate. Well, let's see what I get when I do that. I take the ln of that number, and I divide by that rate, 0.00496292236, and I get t equals 43.290 years. And remember, this is years since, when was Kyoto? Kyoto was 1997. So if I add this to that, plus 1997. I'm at 2040. On our current trend, we have only until 2040. This is 2018. You've got 22 years. Hey, guess what? You guys will have kids and jobs and be all adulting in your lives, and you're going to have to deal with this. This problem is going to fall to you to solve, to deal with. Good luck. We really hope you solve it well. Okay, question number 4. A colony of weevils. A colony of weevils grows exponentially. At the start of the week, there are 1,000 weevils. And if you don't remember what a weevil looks like, just look at the worksheet. There's a picture of a weevil for you. By the end of the week, there are 1,750 weevils. How long will it take to triple the population? Well, I'm interested in tripling the initial population. That's what we're talking about when we talk about tripling the population, tripling the initial population. Okay, so I want to know when there will be 3,000 weevils. That's my goal in this problem. But first, I need to build my weevil population model. Well, luckily, we've got an initial amount, so we can say P equals 1,000 e to the RT. And now we can plug in this second ordered pair to help us find our rate. So 1,750 equals 1,000 e to the R times 7. If I divide both sides by 1,000, I get 1.75 equals e to the 7r. At this point, I have to take the ln of both sides because I've isolated that exponential, and now I can bring down that power. So I'm going to have the ln of 1.75 equals 7r. And therefore, my r is going to be the ln of 1.75 divided by 7. ln of 1.75 divided by 7. I get the rate is supposed to be 0.0799451126, or growing at approximately 8% per day. 8% per day. That's growing pretty fast. Okay, so what have we asked? We want to know when we have triple the original amount, or 3,000 weevils. So I want to know when 3,000 equals 1,000 e to the 0.0799451126t. I'm setting my weevil population model equal to triple the original population. And notice what happens when we divide by 1,000. We get 3, as in triple the population, equals e to the 0.0799451126t. Hey, what are we going to do now? We're going to take the ln of both sides. And when I'm looking at this ln of 3, it's actually making me think of the half-life shortcut. Wasn't the half-life shortcut ln of a half divided by the time for half-life? Look here, we're tripling the population and we have an ln of 3. And you know, if we were trying to double our investment, this point in the problem it would say ln of 2. So watch out for that as you go through these problems. In our problem though, we just need to bring this power down in front. So we'll have ln of 3 equals 0.0799451126t. And to get t by itself, I'm just going to divide both sides by the rate. 0.0799451126. Well, what time do we get when we do that? ln of 3 divided by that rate. I get t equals 13.742. And remember the units on weevil population growth was measured in days, not years. So after 13.742 days, we'll triple our original population. Less than 2 weeks to triple the original population. Watch out for the weevils. Okay, problem number 5. My car depreciates at 6% per year. Okay, so now this is one of those places where we've just done a ton of PERT problems. And you could use PERT here, but I'm going to use this one, A equals P 1 minus R to the T. Because they told me my car depreciates at 6% per year. And, you know, the way I look this up is online. I go to Kelley Blue Book and I look at the value of my car, and it really only changes once a year. It's not incrementally changing continuously. It's not like there's a little meter in the on the side of the car that says the value of the car is this right now, and I could look at it continuously and see it slowly decrease. So I like using this model here, where my R is 6% per year. Yes. So, and the initial value was 28,000. So I think the value of car model looks like 28,000, 1 minus 0.06 to the T, or A equals 28,000, 0.94 to the T. Okay, there's my car depreciation model. I plug in a number for time, and I'll get out the value of the car. Now this problem, though, says I want to sell the car when it still has 30% of its original value. 30% of its original value. Well, originally, the car was worth 28,000. And I want to know when A equals 30% of 28,000. Okay, so let's figure out what that is. But, you know, I don't actually want to take out my calculator and do that. I want to instead go back to this equation, 28,000.94 to the T, and I want to replace A with this stuff. And the reason I want to do that is what's going to happen next. I'm going to divide both sides by 28,000. And I can see that the 28,000s cancel, leaving me just 30% of its value, equals 0.94 to the T. How do I bring that T down? Well, I'm still going to take the ln of both sides and bring that power down. But when I bring that power down in this problem, there's the ln of 0.94 here. This is not the ln of E. It doesn't turn into 1. It's here. So if I'm going to solve for T, I need to divide both sides by the ln of 0.94. So what's that going to give me? T will equal, I'll pull out my calculator and say the ln of 0.3 divided by the ln of 0.94, and I get 19.458 years. I can have the car almost 20 years before I can sell it. Well, that's fabulous if it holds on to value like that. Good job. Okay, number 6. How old is the mummy if it has lost 49% of its carbon-14? And I'm supposed to use 5730 as carbon-14 half-life. Okay, we've lost 49%. That means the object still has, this mummy still has 51% of the carbon remains. 51% of carbon remains. And do you remember what we said about carbon? We said that, about percents. we said that percent was equal to Q over Q sub O. So if I start off with Q equals Q sub O e to the kt, and I divide both sides by Q sub O, I end up with Q over Q sub O equals e to the kt. Now notice over here, we have Q over Q sub O, and that's what we said percent was. So if we have 51% remaining, then I'm going to say 0.51 equals e to the kt. So what I need to find now is k. Well, remember we have that that shortcut for half-life. So the carbon-14 half-life rate is ln of a half over 57, and I said to use 5730. Okay, so what do we get? We get 0.51 equals e to the ln of a half over 5730 t. And this is what we want to solve to find out how old this mummy is that has 51% of its carbon remaining. So I'll take the ln of both sides. I'll bring this power down in front. We've got ln of 0.51 equals ln of a half over 5730 t. Okay, well now I need to solve for t. I'm going to multiply both sides by 5730. And I'm going to divide both sides by the ln of a half. And no, you can't cancel out these ln's, so don't do that, please. Okay, on the right-hand side, though, we've got lots of canceling. ln of cast cancel, 5730s cancel, and so we're left with just t. So t equals 5730 times ln of 0.51 divided by ln of a half. I end up then with t equals 5566, not 0.66, 5,566.299 years old. That is an old ruler. This mummy is 5,566.299 years old because it has 51% of its carbon remaining. Okay, that was problem number 6. Let's take a look at problem number 7. Problem number 7 deals with tuberculosis. It seems last year approximately 1.4 million people died on the planet from tuberculosis. In 2000, let's call that time equal to 0, there were 16,309 new cases registered in the United States. In 2012, 12 years later, we had 9,945 cases. Well, that's great to see tuberculosis in the United States going down. It's pretty infectious, and we'd love to get rid of that. At what rate are infections decreasing in the U.S., and how long until we have only 100 people getting infected each year? Okay, well, let's take a look. We've got our initial amount. So we can start by saying P equals 16,309 e to the RT. And then we can plug in our second point to help us find our rate. 9945 equals 16,309 e to the R times 12. I'm going to divide both sides by this 16,309 to get my exponential by itself. So I've got 9945 divided by 16,309. And that leaves me with 0.609786077 equals e to the 12r. At this point, we've been taking the ln of both sides of the equation. so we can bring this power down in front. On the left-hand side, we've got the ln of 0.60978660077. And on the right-hand side, we've got 12r. So if we divide both sides by 12, we should be able to find the decay rate, or the rate at which people are being infected is decreasing. So the ln of that number divided by 12, and I get negative 0.04122059992 is our rate. Notice about 4.1% is the rate at which tuberculosis cases are being registered in our country. So if I build my tuberculosis population model, it's 16309 e to the negative 0.04122059992t. So this was the answer to part A. Part B says, when will there only be 100 people being infected per year? Okay, so let's take a look at that. Does 100 go in here for time, or does 100 go in here for P? 100 is the number of people who are infected, so I'm going to put that in for P. I need to divide both sides now by that 16309 again. So 100 divided by 16309 gives me 0.00613158838 equals, and on the other side of the equation, we've got e to the negative 0.04122059992t. You know what's coming next because you've done a lot of these problems. We take the ln of both sides so that we can bring this power down in front. Okay, we bring the power down in front. We've got the ln of 0.00613158838 equals negative 0.04122059992t. I need to divide both sides by that rate to get t by itself. So what will that leave me? ln of 0.00613158838 divided by negative 0.04122059992. I end up with t equals 123.586 years. It's going to take a long time to get the number of tuberculosis cases down to 100 per year. It's going to take almost a century and a quarter. Okay, let's take a look at problem 8. Problem 8 is a little hard to understand. It says that the tinted glass reduces sunlight intensity by 20% per millimeter of thickness. Write a model that models intensity, initial intensity 1 minus 0.20 to the t. Oh, x. Sorry, this is a function of x. X. Okay. X is the thickness of the pane. I sub O is the original intensity. And so we can plug those values in. I see them in the third and fourth line of the problem. 15 millimeters thick with an initial intensity of 6,000 watts per square meter. So I equals 6,000.8 to the, and we said this thing was going to be 15 millimeters thick, and that's our x value. Well, the setup is really quite simple. The words seemed a little confusing, but the setup was simple enough. 0.8 raised to the 15 power. And so I end up with the intensity would only be 211.106 watts per square meter. All right. Yeah, that was pretty simple and straightforward. Let's move on to 9. 9, you have $100 to invest, compounded quarterly. So P sub O equals 100, or P equals 100. I'm going back to original PERT. P equals 100. Compounded quarterly means N equals 4. My rate is 2%, so 0.02. So if I build my model for the amount of money I have, that model would look like 1 plus 0.02 over 4 raised to the 4t. I know many of you don't like to leave this in that unsimplified state, so I'm going to do 0.02 divided by 4, and I get A equals 100, 1.005 to the 4t. There's my model for the value of my money. How long would it take for us to have $10,000? Do I plug a 10,000 in here? No, it's not how much money will I have in 10,000 years. It's when will I have $10,000. I'm going to plug in 10,000 for the amount. 10,000 equals 100, 1.005 to the 4t. I'll divide both sides by 100 now. And I'll get 100 equals 1.005 to the 4t. And just like in all those other problems, I'm going to take the ln of both sides, so I can bring this power down in front. But unlike a lot of the problems we've done so far, 4t ln 1.005, this didn't disappear. It's still attached to the 4t with multiplication. So if I need to get t by itself, I need to divide not just by that 4, but also by that ln of 1.005. So 4 ln 1.005. Now, remember, everything in the denominator has to be in parentheses when you use your calculator here. ln of 100 divided by parentheses 4 times ln 1.005, close 2 parentheses. And I end up with t equals 230.834 years. I hope you're not in a rush for your $10,000. It's going to be a while. You might think about investing more money now. Okay, number 10. I kind of want to see what you do with that. This is a very open-ended question requiring some exploration. Many students who have things to do are going to skip this problem because they know 1 or 2 wrong will get them full credit. But this is an interesting exploration to see if you should invest more money or get a better interest rate to make $1 million the fastest. Okay. Finally, number 11. Number 11 requires us to use a formula we haven't used all that much, y equals a times b to the x. Now, we've got 2 ordered pairs in the first problem, 0, 4, and 2, 28. If I remember, these are x and y values. So if I plug in my 4, a times b to the 0. B to the 0 is 1. 1 times a is a, equals 4. Well, that's great. I know what a is equal to, but I still need to find b. Luckily, I have this second ordered pair. So I'm going to plug the second ordered pair and my a back into this original model to write 28 equals 4 times b to the second. Well, that means I need to divide both sides by 4. 7 equals b squared. Now, come on, lazy bones. Come on, sleepyheads. Don't you be taking the ln of both sides here. This is not that problem. This is b is being squared. I need to undo squaring. I need to take the square root. So root 7 equals b. 4 was a, root 7 was b. My model then is y equals 4 times root 7 to the x. And if you don't like that square root, remember we could write this as 7 to the 1/2 power to the x, or y equals 4 times 7 to the 1/2 x. There's my exponential model for this first graph. Okay, last problem. Let's see if we can get this done. This uses the points 1, 3, and 2, 7/3. I'm still going to start with y equals a times b to the x. But notice neither of these x values is 0. So I'm not going to be getting my a value as a freebie like I have in so many of these problems by redefining the first term as 0. All right, so what can I do? Well, I can plug in an x value and a y value, and I'll see 3 equals a times b to the first. And I can do that with this ordered pair as well and say 7/3 equals a times b to the second. Now I've got two equations with two unknowns. That's a system. And I remember that we could solve a system with elimination. I'm going to eliminate not by subtracting one equation from the other, but by dividing one equation from the other. Divide. Look, I eliminate the a's. 7/3 divided by 3 becomes 7/9. And over here, this b cancels one of these, giving me my b value. Well, that's great. I know what b is equal to. All I need to do is find a. And because I'm using elimination here, I can plug this b back into either of these equations to help me solve for a. This bottom equation looks easier, so I'm going to use that one. 3 equals a times 7/9, right? Because b is equal to 7/9. I'll multiply both sides by 9/7, and I end up with 27/7 equals a. So my equation then for this graph would be 27/7, 7/9 to the x. Let me write that again. Y equals 27/7, 7/9 raised to the x power. There it is. Ew, but perfect. And not so hard to do even without a calculator. I hope this helps answer some of your questions about exponentials on parade, and I look forward to talking to you about more exponential problems when we come back from Thanksgiving next Monday. Hope you have a great Thanksgiving weekend, everyone. Remember, the deadline for all makeups is a week from, the end of the first week of December. So make sure you keep that in mind when you are thinking about how to spend this weekend. Take care.